are you able to?
So, yes, we can see your presentation. So let me introduce our speaker. So Professor Usha obtained her PhD from IIT Madras, and she was a professor at the Department of Mathematics in IIT Madras for many decades. And currently, she's a emeritus professor at the Department of Mathematics in IIT Madras. Her area of research is in hydrodynamic stability, and in particular film instability in open flow and confined geometries, and modeling the nonlinear dynamics in these flow systems. Welcome, Professor Usha, and please go ahead. Could you please make your window in presentation mode?
Has it not appeared in the presentation mode?
I think maybe if you go to window or edit, or maybe I forget the shortcut.
Control L.
Yes, it's Control L. If you just press Control L, it should work. Okay, yes, it works. Thank you very much. Please go ahead.
Thank you. Thank you very much for the introduction, and
just wanted to confirm the recording part is fine.
yeah, okay.
Okay. Thank you.
Yeah. Thank you very much for inviting me to be a part of this symposium. I'm very happy to be a part of it. And I would be sharing my collaboration with Dr. Geetanjali and Professor Naveen Tiwari of IIT Kanpur in this talk, which is based on a new perspective which we had thought about in the case of modeling of dynamics and stability of thin film flows down inclined planes. So this has appeared in Physics of Fluids in 2020, and the falling liquid films have been a topic of fundamental and applied research for several decades since the pioneering experimental work by Kapitsa in 1948. And this is a convectively unstable open flow hydrodynamic system. And as you see in these pictures, it displays a rich variety of spatio-temporal structures and also a sequence of wave instabilities and transitions. And these are generic to a large class of hydrodynamic and nonlinear systems. The pictures that you have seen are all experimental predictions by Alexei and Co, and the earlier ones are from Liu and Goloub's experiments. And although you see the structures in the earlier pictures to be very complicated, it is possible for one to still identify robust coherent structures, namely solitary waves, in thin films that appears to be a randomly disturbed surface. And these solitary waves interact with each other continuously, and therefore falling liquid films can serve as canonical systems for study of spatio-temporal chaos. Further, falling liquid films are typically associated with low flow rates and low pressure drops, small thermal resistances, and large contact area per unit volume. So it's not a surprise that falling liquid films play a central role in a wide spectrum of engineering applications that includes cooling and coating processes. And therefore, there is a need for accurate understanding of the hydrodynamics of this class of systems, because it is crucial in the design of devices that exploit falling liquid films. And it is with this in view that several models have been developed, and extensive work has been done, and these studies can all be viewed in the review works by Oran and Davies in 1997 and Craster and Matar in 2004, and also the nice book by Chang and Demikin that has been published in 2002. So what do these investigations tell us? The results tell us that the solution is unstable to long waves. If the Reynolds number exceeds 5/6 into cot theta, where theta is the angle of inclination of the inclined plane to the horizontal. So solving Navier-Stokes equation with a free surface which is unknown a priori is a difficult one. It's very hard to handle. And the interest is only in how the film evolves, namely determining the free surface thickness and not on the flow field. And therefore, the efforts have been towards deriving model equations for the evolution of the film thickness. The pictures that we have seen clearly show us that the space-time evolution of waves are slow at low to moderate Reynolds numbers. And in addition, we also observe that the internal fluctuations that we have observed, they remain slaved to the local film thickness H. So this suggests that one need not solve a three-dimensional problem. One can completely eliminate the cross-stream velocity from the velocity field. So this reduces the three-dimensional problem to a two-dimensional problem. This can further be simplified to one-dimensional problem so long as the secondary instabilities do not introduce any span-wise modulations. So what happens? We have a long wave character of instability, and hence the length scales of the free surface perturbations are large compared to film thickness. So that helps us to introduce a small parameter. Suppose I call it epsilon. So we introduce a small parameter so that we will be able to scale down these downstream derivatives with the help of this small parameter. So all these features that we have listened to so far, right, suggest that we should be able to employ a modeling strategy that makes use of this long wave character, namely that there is a small parameter epsilon, and Benny made use of this modeling strategy. So it expanded all the flow variables in terms of the small parameter epsilon, and under the assumption that the flow variables are all asymptotically enslaved to the evolution of this film thickness H, and he ended up with a one equation model. And this equation had an unknown. The only unknown was the film thickness H, and this is referred to as Benny's equation. And this is a one equation model that describes the evolution of film thickness of a thin film over an inclined substrate. But unfortunately, there are drawbacks in Benny's model in that the solution has a finite time blow up not far beyond the threshold, in spite of the regularizing effects of the surface tension. So there were efforts to cure this drawback by including higher order terms, right, when the expansion with respect to epsilon is considered. However, or a Paderi summation technique was employed, right? But all these did not yield satisfactory results. They ended up only in underestimating the amplitude and wave speed of the solitary waves. So what do we get as the message from one equation model? The one equation model is not at all capable of describing the dynamics of this thin film sufficiently far from the threshold. And therefore, it is of no use taking the one equation model, namely that developed by Benny, and describing the dynamics Although the only one advantage from here is that it could correctly predict the instability threshold, but it could not, I mean, there was a finite time blow up. So the suggestion was that why not consider system of equations, right? With one of the unknowns to be this film thickness h, and the other unknowns can be average quantities that are associated with this thin film dynamics. And one such quantity is the local flow rate Q, which is integral across this film of thickness h, the velocity along the mainstream direction, namely u, integrated with respect to the cross stream direction, namely y. So Skedov took this suggestion and developed a two-equation model with two unknowns, one of them being the thickness, which is the local thickness, and the other one is the local flow rate, namely Q. And his assumption was that, what did he do? He started with a streamwise parabolic profile U. And he made use of this, integrated the streamwise momentum equation and the continuity equation by taking U as this. And he ended up with the evolution equation for the unknowns H and Q, which are these two equations. And what was his assumption? The assumption was that the velocity remains self-similar and parabolic even out of equilibrium. That was the basic assumption that was underlying Skedov's model. But again, this two-equation model had some limitations. Namely, it could not predict the instability threshold accurately. The instability threshold predicted by Benny's model is 5/6 cot theta. Not only Benny's model, the experimental predictions also gave the result as 5/6 cot theta. But Skedov's model predicted it to be simply cot theta, and therefore the prediction was erroneous, although he took into account two unknowns h and the local flow rate, right? But when b equal to 0, that is for a vertical wall, his prediction trivially was correct, that the flow is unstable at all Reynolds numbers, but the limitation in the model showed up, right, while describing the nonlinear evolution. So what was the reason for this failure of the two-equation model? It was attributed to the lack of flexibility of the assumed parabolic profile, right? That is, the flow remains parabolic even out of equilibrium was the basic assumption in the development of Skedov's model, and that did not give any flexibility to the model, and it cannot remain parabolic as the film evolves. So there will be some deviations. Being a thin film, the deviations should be properly accounted for while taking the velocity ansatz. That did not happen when Skedov assumed that the velocity is self-similar and it is parabolic. So people tried to cure this failure by assuming some generalized parabolic profile and parabolic profile with Pade approximation and other things, but they were not successful. And the experimental observations and the numerical predictions clearly said that there are deviations from the parabolic profile, and that is the cause for reason of Skedov's integral boundary layer model. And so following this, right, there are several investigations, as I said, by taking the general parabolic profile or the energy integral approach in which the energy balance is accounted for, or a self-similar parabolic profile and a Galerkin projection was considered in central manifold analysis, right? All these did give the instability threshold correctly, accurately. However, the quantitative predictions with regard to the wave speed and wave height were not as accurate as predicted by the experimental observations. Then Ruyer-Quill and his group developed weighted residual technique, which Dr. Sangashri also spoke about. this weighted residual technique was able to predict as close as possible to the non-linear wave characteristics, and that becomes the standard technique of solving thin film flow problems down inclined substrate by taking into different aspects, right, associated with practical applications. And recently, Amaush and his group of, his group worked on a model where they considered the double weighted residual integral boundary layer model developed by Ruerquill and his group. But they introduced a free parameter, right, which helped them to refine the velocity profile, and this free parameter provided this free parameter acted as a parameter which can be tuned to get the desired wave characteristics. And they had shown that there is a substantial improvement in the predictions in the inertia dominated regimes. So this gave us some motivation. We require a profile which is not a parabolic profile, and there should be a refinement of this parabolic profile in the sense that there should be a free parameter in the profile that we may choose for velocity ansatz, so that that free parameter can be chosen in such a way that we will be able to tune that parameter to achieve the desired wave characteristics. And the profile should not be a parabolic profile. That was one motivation. The second motivation for our work came from the squeeze film dampers performance, right, by the squeeze film flow models, namely the energy integral model with ellipse profile considered by Hahn and Rogers in 1996. And they had shown that by taking an ellipse profile as a weight function and perform the energy integral model, namely which accounts for the energy balance while integrating across the film, then they were able to show that the squeeze film damp force is more accurately predicted, right, for large amplitude motion. So this was the second idea that we could get, and so we thought that why not use an ellipse profile for determining the evolution equation for thin film down an inclined plane and develop a two equation model. The reason being, when we take an ellipse profile, there is a parameter which is the eccentricity of the ellipse, which is intrinsic to this profile. All right, and therefore this eccentricity can be tuned. It should be less than 1 is the condition when we take an ellipse profile, but this must be less than 1 will help us to tune the profile in such a way that we are able to arrive at the desired wave characteristics. So with these two ideas in mind, we thought we would develop an energy integral model with ellipse profile as a weight function and develop a two equation model. So with that in mind, we started our model derivation. Our Navier-Stokes equations with continuity equation are the governing equations, and the boundary conditions are no slip at the inclined substrate, and at the free surface y is equal to eta of x comma t. The conditions are the kinematic free surface condition, the balance of normal and tangent shear stress at this free surface. So we wanted to non-dimensionalize the governing equation. So we took the scales which are based on the time-dependent Nusselt solution, and the corresponding dimensionless equations and the boundary conditions were obtained. So as I said, our goal was to derive a model. We did not aim at developing a model which would be as accurate or more accurate than the standard WRI-BL model. Right, this was our first attempt to derive a model which doesn't involve a parabolic profile, but which should be capable of predicting the linear instability threshold accurately, and which should be capable of predicting the nonlinear dynamics at least like the available standard model. Right, the available standard WRI-BL model is a second order consistent model. So we thought that we would be happy with the first order consistent model, which should be capable of predicting the instability threshold accurately, and which should be able to capture the nonlinear dynamics. And I mean, what is the in nonlinear dynamics as accurately as possible. With that as goal, we started working on the details. That is, as I'll repeat again, our goal was to develop a two-equation model which is first order consistent, such that it's going to be a two-equation model describing the local film thickness and the local flow rate. The model would be taking care of the energy balance, and it will be using the ellipse profile, and therefore there is eccentricity which is intrinsic while taking the ellipse profile, which can be tuned to get the desired characteristics. So so that our model should be able to capture the results which are already available. Does it perform as good as the available models? Once we are satisfied with that, we can work more on that and develop better models so that we are able to get the desired characteristics as predicted by the experimental observations. So with that as goal, we worked to derive the ellipse profile. So we took the equation of the general equation of the second degree equation and then applied the boundary conditions first and got the profile. And this we wanted to use as the weight function as in Galerkin approaches. So the no slip condition at the substrate and the no shear stress at the free surface, when applied here, gave us the profile as this, and which can be written in the form of an ellipse as this, which told us that the ellipse profile, which satisfies the conditions that we have laid down, has major axis as kp square into a square, minor axis as a square by 4, which are related by b square equal to a square into 1 minus e square if the equation of the ellipse is x square by a square plus y square by b square equal to 1. So when we do that, we see that this is the eccentricity of this ellipse profile that is expressed in terms of this free parameter a. And therefore, by varying this value of the parameter a, which can be tuned with the condition that E remains less than 1, we should be able to arrive at our model which is capable of capturing the instability threshold accurately and which performs as good as the available models as far as the nonlinear dynamics is concerned. So we varied this value of A, and we observed that the eccentricity, as A is increased, the eccentricity increases and it approaches the value 1. And so this parameter A modifies the ellipse profile, and so it serves as a free parameter which can be tuned to achieve the desired wave characteristics. And we observed that the velocity exhibited a non-monotonic trend as A increases. So the velocity for A equal to 40 was between A equal to 20 and 60. So we took the value of A equal to 40 in our computations. This is not the only reason why we took A as 40. From the nonlinear analysis also, we would be able to show that A equal to 40 is an appropriate value of A with which we can work so that we are able to get our desire, we are able to achieve the desired goal. So what did we do? We took the ellipse profile, we multiplied the x momentum equation with u so that the energy balance is accounted for, integrated across the film thickness, and we ended up with the two equation model, right, involving the local film thickness capital H and local flow rate, which is capital Q. So this being the evolution equation, we wanted to see what does it give for the instability threshold. So we imposed infinitesimal two-dimensional disturbances of the base flow, right, in order to determine the instability threshold predicted by this model. And we ended up with the evolution equation as this. The first four terms in this equation contribute to the inertial effects. This term and this term tell us about the pressure and the surface tension effects. The term over here, namely eta hat suffix t, that arises due to gravitational acceleration, and the last term is due to the shear stress at the wall. So we took a wave-like disturbance, which is a sinusoidal disturbance, and substituted it in the evolution equation and ended up with a dispersion relation, which is a quadratic equation for the complex phase velocity, c, which is complex. The real part gives us the phase speed. The imaginary part gives us the linear growth rate. So when the linear growth rate Ca is greater than 0, the flow is unstable. Ca less than 0, the flow will be stable, and Ca equal to 0 will give us the neutral boundary, which splits the parameter regime into stable and unstable regions. So we drew the marginal stability curve by taking Ci equal to 0. That ended up and gave us the instability threshold as cot theta by Re equal to the right hand side, which depends on this parameter capital A. So we wanted to plot this cot theta by Re, right? We saw that cot theta by Re asymptotically approaches this value 1.2, which is the critical value predicted by the available standard model, which is the weighted residual integral boundary model, and the energy integral model by taking parabolic profile as the weight function. So we named this model as EIME to say that it is the energy integral model, and the ellipse profile is the weight function. So I refer to the model as EIME. So this EIME model demonstrates its capability to predict asymptotically the accurate value of cot theta by Re, which is equal to 1.2, which was predicted by the experiments as well as the available standard model. And whereas the momentum integral model, namely that was predicted, that was derived by Skedo, could not predict this value because of the lack of flexibility of the parabolic profile. So we wanted to compare the phase speed and the linear growth rate with the available experimental results, the nonlinear simulations of the Orr-Sommerfeld system, and you can see the pictures. We have compared with different models as well as the available experimental results, and we observe that the EIME model follows the trend, and it is in close agreement with the available experimental observations as well as the available standard model predictions. So the comparison of the wave speeds, which you have seen in the earlier slide, with the experimental observations for a vertically falling film clearly shows that the experimental observations and the EIME model, right, are very close to each other for moderate Reynolds numbers. Further, the approximate solutions which were obtained by Kranz and Goren, right, and the conclusions based on his approximate solutions match with the current model's result. Also, the direct numerical simulations of the Orr-Sommerfeld equations performed by Pearson and Whittaker and his conclusions are confirmed by our model. And the close agreement of our model with experimental observations clearly supports the validity of the linearized theory in the parameter regime. Reynolds number is of order of 1 by epsilon, which means for moderate to large Reynolds numbers, our predictions are accurate and they agree, and they are in close agreement with the experimental observations and the standard model predictions. Then we compared the spatial growth rate of linear waves as a function of wave number, and compared with the WRABL model, and we observe that it performs as good as the WRABL model, and also the squares that are marked are experimental predictions by Liu and Golub in 1994 for small wave numbers, and our model results follow this trend, and therefore it confirms the validity of the model at long wavelengths. And so we moved on to having been satisfied with its performance in the linear regime, we worked on the nonlinear evolution of the free surface. So we tried to understand the existence and properties of the nonlinear two-dimensional waves generated by this model beyond the threshold for instability. So full numerical solution of the coupled nonlinear equation was performed in a computational domain of length 2 pi, sorry, with a uniform base state of unit thickness. And we examined the growth of initial sinusoidal disturbance to the base state. And this was done using finite element method and employed the commercial software Cosmol. And we determined the growth of the perturbations by employing a measure psi, which was log norm h minus 1 by psi naught, where the norm is L2 norm defined over the computational domain, and psi naught was norm h evaluated at t equal to 0 minus 1. That is the magnitude of the perturbation given to the primary flow. And our computations were performed by requiring that it should be accurate to 10 to the minus 7. And we determined the solution of the time-dependent evolution equation by imposing the periodic boundary conditions. The figure on the left panel shows the nonlinear growth rate for different values of cot theta by Rd, while the figure on the right panel gives you the comparison of the slope of the nonlinear growth rate with the linear growth rate, which was obtained from the linear stability analysis. So the black squares which are marked on these lines, they are the linear stability results for the growth rate, slope of the growth rate. And the nonlinear growth rate, slope of the nonlinear growth rate was compared with the slope of the linear growth rate using this measure, and we observe that the linear stability predicts the growth accurately at the initial time. And further, the growth rate predicted by the nonlinear simulation and linear stability agree very well is what we observe from this figure. So this clearly shows us that the eigenvalue analysis, namely the linear stability analysis that we have performed, is capable of providing the physical insight about the instability in such flows. So we went on to draw the nonlinear evolution, namely film thickness as a function of x, namely the streamwise coordinate at different times, and we observed that as time progresses, the amplitude of the disturbance that was given to the system decays, and the thickness of the film ultimately reaches the base state thickness. And clearly this indicates, as Liu remarked, that the instability is of convective type. I recall my statement earlier that the falling liquid film is a convectively unstable open flow system, and our results clearly indicate that the instability is of convective type. So as a result,
Professor Usha, sorry to interrupt, but could you maybe complete in a few minutes, couple of minutes?
yeah, another 2 minutes I'll be completing.
Okay, no, yes, no problem.
Yeah.
Thank you.
So as a result, what happens to the perturbations? Perturbations leave the computational domain, so after they are introduced, indicating that the instability is of convective type. So these are all the results of nonlinear simulations. And we also plot the maximum film thickness and the minimum film thickness as a function of time, and we were able to show that there is a decrease in the absolute deviation from the base state as cot theta by RD increases. And this indicates that there is destabilization of flow because of the imposed perturbations. And you recall the earlier picture that I had shown also exhibited this behavior, and the result by predicting the maximum and the minimum thickness reflects the earlier results where we have drawn the nonlinear evolution. So highlighting the highlighting the results or outcome of this simple first order consistent model by taking a profile, right, which has a free parameter which can be tuned in order to achieve desired characteristics. We can say that our model's performance is quite satisfactory in the linear regime, and it is also quite satisfactory in getting the behavior of the nonlinear waves at a moderate distance from the instability threshold. As I said, the value of the parameter A, the free parameter A, which is intrinsic in the ellipse because it is related to the eccentricity of the ellipse, right? Taken as the weight function, right? You remember I had told you we have taken our in our computations A is equal to 40. I had given the reason with coming from the base velocity. Now we were able to also choose the value of A based on our nonlinear simulation, because we were able to see that when we took the value of A equal to 40, the results were such that we were able to observe closeness of the linear growth rate and the phase speed for this value of A to the available experimental observations. And this choice has also been justified by the value of the linear growth rate derived from the nonlinear analysis, and therefore the reason for choosing the free parameter value as A equal to 40 is justified. And we have been able to show that the model's performance is as good as the available standard models, namely the weighted residual integral models. But there are limitations of this model. What is it? It is a first order consistent model in both inertial as well as viscous terms. And this model may not be able to, using this procedure, we may not be able to get a second order consistent model for the simple reason that the profile that we have taken is not a self-similar profile. And therefore, the model that we may get as a second order model by incorporating second order viscous effects will be a model which takes into account the second order effects of the viscous terms, but it will not be able to capture the nonlinear characteristics correctly for the simple reason that the model equation will not have the required structure to capture the nonlinear wave characteristics. And therefore, something more has to be done. Taking this ellipse profile itself, something more has to be done in order to get an accurate model which is second order consistent, right? Then next, the model cannot capture the transition to absolute instability because the model is based on long wave analysis. So all these three issues have been addressed in our recent work, which is based on a new model that uses the suggestions given by the perspective which came from this work presented in this talk. And that work has also been accepted for publication in JFM, and you may look up as soon as it is published. Thank you very much for your patient hearing, and thank you for giving me this opportunity to share this. The reason for taking this as my topic of lecture is that you had written to me that there are research scholars who would be interested to learn more on this topic, and I thought that now that a new perspective is given, they should be able to work on with this perspective and develop better and better models that will be able to capture the nonlinear characteristics. Thank you very much for your invitation, and thank you all for patient hearing.
Thank you very much, Professor Usha, for your very nice presentations, and also congratulations on all your new results. So if there are any questions now from the audience, maybe there is some time for a couple of quick questions. Please go
Yep.
ahead.
Yeah. Yes.
If you have any questions, please unmute yourself and you can ask your question.
Hello.
Yeah.
Yeah, ma'am, thank you so much for this beautiful presentation. I mean, I just have one generalized question regarding these limitations as you were talking about. So, ma'am, generally, I mean, whenever I went through few literature, so there is a basic comparison between linear stability analysis and general linear stability analysis. So, few researchers have reported that many a times a general, linear stability analysis, long wave linear stability analysis, over predict the results. So, ma'am, what is your take on this? That why this happens in those cases, or whatever cases they are talking about? I mean, in general, what are your perspective about this?
What is the model that they have employed? Is the question is a question to be answered.
Okay. Let's say suppose in case of porous medium Darcy-Brinkman equation, or in case of suppose this liquid crystals also, I have came across this kind of issues people have mentioned.
Because it is there is an assumption that there is a small parameter epsilon that is involved in the long wave analysis, and you are truncating the series expansion by considering, say, terms only up to order of epsilon, or terms involving order of epsilon square, and so on, depending upon the number of terms that you take into account in your analysis, right? The accuracy with which you want to get your results, finally that is going to affect the result that you capture at the end, isn't it? As I said, what was the limitation in Benny's model? In Benny's model, there was a finite time, singularity in his solution. The reason being, he only took terms up to order of epsilon. Higher order terms with which helped to cure also did